Motion in 2 and 3 dimensions. Most real-world kinematics problems involve the motion of objects in 2 and 3 dimensions. This should come as no surprise, since we do live in a 3-dimensional world. Fortunately, most of the equations we derived previously in 1-dimensional motion can be easily generalized to the 2 and 3-dimensional cases. Instead of treating x of t, v of t, and a of t as scalar-valued functions for position, velocity, and acceleration, we will reinterpret these functions as being vector-valued. In other words, instead of the value of x of t at a particular point in time being a number or scalar, the value of the function at that point will be a vector. Motion in a plane. Motion with uniform velocity in a plane. Consider a point object moving in xy plane with a uniform velocity vector v. Let us suppose O be the origin for measuring time and position of the object. Let the object be at position A and B at timings t1 and t2, where vector OA is equal to r1 and vector OB is equal to r2. The displacement of the object after a time interval t2 minus t1 is vector AB. According to triangle law of vectors, vector OA plus vector AB is equal to vector OB, or vector AB is equal to vector OB minus vector OA is equal to vector R2 minus vector R1. If the position coordinates of the object at points A and B are x1, y1 and x2, y2, then vector R1 is equal to x1i plus y1j and R2 is equal to x2i plus y2j. Therefore, vector R2 minus vector R1 is equal to x2i plus y2j minus x1i plus y1j is equal to x2 minus x1 into I plus y2 minus y1 into j. Therefore, displacement of the object in time interval t2 minus t1 will be vector AB is equal to vector R2 minus vector R1 is equal to x2 minus x1 into I plus y2 minus y1 into j. Since velocity is equal to displacement by time taken, therefore vector V is equal to vector R2 minus vector R1 by t2 minus t1. Since the object is moving with a uniform velocity, this value of velocity is the same for all values of t1 and t2. So, equation of motion vector R2 minus vector R1 is equal to vector V into t2 minus t1, or vector R2 is equal to vector R1 plus vector V into t2 minus t1. Let us consider at time t is equal to 0 and the object be at A, and the position vector with respect to O be vector r0 and x0, y0 be the coordinates of point A. Let the object go to point B, x, y after time t, whose position vector with reference to O be vector r. Then, replacing vector r2 with vector r1, vector r1 with vector r0, t2 by t1 and t1 by 0. Then we get vector r is equal to vector r0 plus vector v into t minus 0 is equal to vector r0 plus vector vt. Let Vx, Vy be the magnitudes of the components of the velocity vector v of the object along x-axis and y-axis respectively. Then, vector v is equal to Vxi plus Vyj, where v is equal to root of Vx square plus Vy square. Also, vector r0 is equal to x0i plus y0j, and vector r is equal to xi plus yj. Putting values in, we get x0i plus y0j plus vxi plus vyj into t, or xi plus yj is equal to x0 plus vxt into I plus y0 plus vyt into j. This equation is true only if the coefficients I and j on both the sides of this equation are separately equal. Hence, x is equal to x0 plus vxt and y is equal to y0 plus vyt. Equation of path. The equation of path of the object moving with uniform velocity in 2 dimensions can be obtained by eliminating t from the above equations. So, t is equal to x minus x0 by vx. Putting this value in, we get y is equal to y0 plus vy into x minus x0 by vx. This is the equation of a straight line having slope vy by vx. This is shown by a straight line AB in the figure. Hence, the path of an object moving with uniform velocity in 2 dimensions is a straight line. Motion with uniform acceleration in a plane. Consider a point object moving in a plane with a uniform acceleration vector A. Let us suppose OB be the origin for measuring time and position of the object. Let the object be at positions A and B at timings t1 and t2, where vector OA is equal to vector r1 and vector OB is equal to vector r2. Let vector v1 and vector v2 be the velocities of the objects at instants t1 and t2 respectively. Then, constant acceleration is given by vector A is equal to change in velocity by time taken is equal to v2 minus v1 by t2 minus t1. This value of acceleration is same for all values of t1 and t2. Motion in a plane with constant acceleration. A constant acceleration is a special case of the accelerated motion. Constant acceleration. The constant acceleration is a special case of accelerated motion. There are vast instances of motions which can be approximated to be under constant force and hence constant acceleration. Two of the most important forces controlling motions in our daily life are force due to gravity and friction force. Incidentally, these two forces are constant in the range of motions of bodies in which we are interested. For example, force due to gravity is given by F is equal to Bm m by r square. R square